Okay, topic for today. I decided that we'll talk about just two more topics that's related to inheritance, which is abstract class and also interface. They're somehow related to your lab test this afternoon. They will not be covered, but somehow related. So it can be a nice review as well. Let's do that quickly today, and then on Wednesday, after the lab test, we'll start recursion. That's what we'll do. All right? Okay, let's now review very quickly the problem that we talk about. Okay? So two things we're going to talk about today. One is abstract class. The second one is called interface. So these two concepts, I think, is the best illustrated using examples. So we'll use example to illustrate. The first one, abstract class. Okay? Let's have a look at the problem we have over here. Let's just go over that all together. Let's read it through. Okay? So we have a polygon. So polygon basically is basically a shape with many sides. So polygon may be either a triangle or a rectangle. So we're talking about two kinds of polygons. It can be either rectangle or triangle. So what do we want to perform on a particular polygon, which can be either triangle or rectangle? So we may either want to grow the shape by incrementing the sides. Let's say we used to get 3x4 rectangle. We want to grow it to be 4x5. Okay? So that means growing the size. Or we may want to calculate the parameter for the shape, okay? The summation of the sides. And we may want to compute and return the area for the polygon, which can be either triangle or rectangle. So this is the problem we want to solve. Okay? Now, the challenge really is, the reason that we wanted to use inheritance, like what we did for students, resident students, and non-resident students, is because we can reuse the code from the superclass. So we can eliminate the code duplicates. Okay? We want to do the same thing. So before I show you the let me just show you the formula very quickly. Okay? Now, in order to calculate the area for a rectangle, length multiplied by width, that's straightforward. We cannot certainly apply the same formula, width by length, to calculating the area for triangle. We definitely cannot. Okay? So that means they cannot share the same code for calculating the area between the two shapes. Okay? That means we got to get two versions of calculating the area. Okay? So this is a Heron's formula. You don't have to prove it. Just take it for granted. Also, you don't have to memorize it. I will show you some application of the formula. It's very easy. All you got to do is you have to calculate the sum of all the three sides divided by 2 and use some square root from the math class. Okay? Basically, what this slide tells us is the problem we are facing with. There's certain method we can define that's common to both triangle and rectangle, which is to get a parameter, for example. You just sum up all the sides together, just adding side number 1, side number 2, and add it up side number 3. However, for calculating the area, you cannot use the formula for both shapes. You have to use different formula. Okay? To be more precise, okay, that's a problem we are having. We want to eliminate code duplicates. So let me just show you the overall design very quickly. Okay? And this is why we need something called abstract class. Okay? Let's just have a look. We are going to see 3 classes in total. We got a class called Polygon, okay, under which we got 2 subclasses. One is called rectangle. The other one is called triangle. So we got 3 classes over here, right? You can think about, analogy would be, you can think about polygon is a little bit like a students. Rectangle, triangle are more like resident versus non-resident student. They're simply subclasses. Now, what's really the new thing over here? We want to say for certain methods or attributes, we want to have their definition precisely defined at the polygon superclass level. But for some other methods, we want to leave their implementation unimplemented, just empty, so that they can be overridden at the subclass. Okay, that will highlight it to you. For example, in this particular case, let's say every polygon simply got an attribute called sides, which is going to be an array of double. So sides.length for this particular rectangle would just be 4. We store all the 4 sides. On the other hand, sides.length for this triangle over here would just be 3, an array of 3. Okay? Well, I'll show you an example. And then we want to define how we can grow a particular shape. We simply just increment each side by just 1. That can be done uniformly. And also, how do you get a parameter for a particular polygon? You just sum up all the sides together. Now, the tricky thing is, how can we get the area for a polygon? That's a tricky bit. Okay, let's see how we can do that. Am I losing the connection here? Okay, one moment. Why am I losing my connection for the Apple Pencil? Give me one moment, please. Why is that simply just gone? Apple Pencil here. Yeah, I do have it. Wow, that's pretty bad. Guys, I would suggest the following. Just give me 1 minute. I'm going to fix this, okay? Yeah, but feel free to sketch your back. That's fine. Then give me 1 minute. I'll call you back when I'm ready. Okay, let's see if that will be back. Sorry about that. Hopefully that's back. Okay, good. Okay, thanks for your patience. Now, the only method we're going to make unimplemented at the polygon level is get area. But as far as what we have learned so far, you simply cannot say a method is not going to be implemented. You have to implement every method. So we just need to learn a new keyword in Java, which is abstract. Whenever you put a and the keyword abstract in front of a method, it simply means we are not going to implement it at this class. We expect the future descendant classes of the current class to implement that method, which means when we get to the rectangle level over here, we're going to implement the get area by simply applying W multiplied by length, all right, width by length. On the other hand, at the triangle level, we are also going to override the get area method by applying this formula over here, the Heron's formula. Okay? Any questions so far? It's only showing you the idea, so you will know what to expect in the code. Okay, to sum up, basically there are two kinds of methods we're going to see in the Polygon. Yeah. One kind is we're going to give the definition in complete detail, just like how we did previously. The only thing that's new would be something called abstract, which means at this point for Polygon, since we don't know exactly which formula to apply, so we're going to leave that as abstract, which means unimplemented. Okay? Questions? Or just exactly. Don't implement this method yet. We simply don't know how. Okay? Yeah. Okay, let's have a look at the code very quickly. Okay? Now, let's go over. Okay, and I'll show you some use cases. Static type, dynamic type, polymorphism, dynamic binding. Hopefully you are comfortable with these ideas. You will see those again in these slides. Hopefully that can be a nice review for you for today. All right. Now, the first thing you should notice, we say Polygon is abstract. So that's a new keyword you have to learn. Just one new keyword. The only two new keywords you have learned today. One is called abstract. The other one is called interface. Okay, this is the first one. So we say public abstract class Polygon. And then every polygon simply got an array of double being its sides. In the case of rectangle, it's going to be of size 4. In the case of triangle, it's going to be of size 3. Okay? And then we also got a polygon constructor here. You simply give an array of double to initialize, right? And then simply assign the array. And then to grow the polygon, we just use the same way for both rectangle and triangle. We simply go over all the sides and then increment the size by 1. So that means the triangle, rectangle, they will apply the same version of the method. There should be no difference, okay? Also, we got get parameter. Also, it's very easy. Just sum up all the sides together. Also the same way for rectangle and triangle. Now, here comes the interesting thing. You can see for this method here, what do we put here? We simply say abstract, keyword, double, return type, and get area. You can see there's no curly brackets over here, right? Immediately after the method name and the parameter list, which is empty in this case, we just put a semicolon. That simply means for this class over here, we simply don't have any definition just yet for get area. Okay? There is a direct consequence to this abstract over here. Okay? This is something hopefully that makes sense to you. So now, if I try this, I say this class of polygon here is simply abstract, simply because you got at least one method that is abstract. Okay? Now let me ask you something to test your intuition. Now, if I simply write something like this, let's say we got polygon abstract class already. Okay? Let's not worry about rectangle, triangle just yet. If I say polygon over here, P is assigned to new polygon, let's say. Intuitively, do you think this should be acceptable in compilation? Should it compile intuitively? Yeah, but no, actually, if you know that already, try not to go that way. I want you to think intuitively. If we got something like this, what would be the expectation on P, right? Basically, all the methods we declare in the polygon class, including p.size, p.grow, p.getParameter, also p.getArea, including, because the method was declared over there. So that means one of the expectation would be p.getArea. However, if we allowed this particular line to compile, and then at the runtime we do expect to call getArea on P of static type polygon, what's going to happen in this case? Well, nothing to be applied, right? Simply crash in this case. Okay, so that is why this particular line over here is not going to compile. Okay, that's the reason. So this will simply not work. Every time when you talk about the new keyword, you're trying to put a new dynamic type. The dynamic type must have every method implemented. Cannot be any method that's unimplemented. Okay, that's something that's a little bit new from what we learned previously. Okay, yeah.
So in other words, Polygon has to be abstract to have abstract method.
Yes, yeah. I think so. Yes. So Polygon has to be abstract in order to have abstract method. We can think in this way. Since we got at least one abstract method here, that's why this class is also abstract. Yeah. Good. Thank you. Right. So now let's look at the code. Let's look at the code all together. Okay. And then we'll see examples. Now let's say first of all we have a class called rectangle, and that extends polygon. Also we have triangle that extends polygon. We got two subclasses, right? And then you can see that for the rectangle constructor versus a triangle constructor, let's see what we have over here. We simply use the super keyword over here and the super keyword over here. But let's see what the difference is. In the case of rectangle, we know it has 4 sides. So we simply say new double array of size 4. In the case of the triangle, new double size array of size 3. Right? That's the difference. Okay? And then once we create the 2 arrays accordingly, that means over here in the superclass we got sides over here. In the case of rectangle, we simply create 1, 2, 3, 4 slots of the array. In the case of triangle, we got an array of size 3. Okay? And then we simply say, let's say this. If I simply say a rectangle, and then I would say maybe 3 by 4, which means the length should be 3 and the width should be 4. What it will do is you're simply going to do 3, 4, 3, 4. Okay? Just let's say we just store all the 4 sides. Okay? Just for this particular implementation. And then in the case of triangle, let's say this is what we get. Let's say we got 3, 4, and 5. Right? So that means we got side number 1 is 3, side number 2, 4, and then 5. In that case, we get 3, 4, and 5. Okay, so depending on what the instance we want to create for Polygon, we're gonna initialize the array differently. Okay. Okay, any questions until now? We're good, right? Now here comes the highlight. You can see get area over here, get area over here. So these are not abstract anymore, whereas used to be abstract at the superclass. So now, in the case of the calculation for rectangle, what we have to do is we simply say the first side multiplied by the second one, 3 multiplied by 4. Okay, that's easy. And for get area for the triangle over here, we simply apply the formula. Okay, I'll just show you the formula again very quickly. And then you can double check the code to make sure it's doing exactly that. So that's the formula over here. You have to calculate the summation of the 3 sides divided by 2, and then multiply them all together and take the square root. For square root, you can simply use a math class. So this part here is not difficult. Okay, so that's exactly what this part will do. So I'll leave you to double check to see that's doing that. Okay? Any question until now about the abstract class? We got 3 classes over here. Polygon, and we got, in the Polygon class, we simply get area is simply abstract. And then in the subclass, rectangle and triangle, we basically reuse all the code for grow. We use the code for get parameter verbatim. The only thing we try to add to override is the get area over here at the subclass level. Okay, guys, any questions until now? Yes?
Could you go over the super?
Yeah, of course. The super keyword over here, okay, you can definitely also see some similar usage for the resident students. Super over here, super over here. If you have super and get parentheses already, that means you're calling the version of constructor in the superclass. The super over here is calling exactly this Polygon constructor. So this guy over here is basically super, which expects an array of double, right? In the case of the rectangle, I simply pass an array of size 4 and then fill them up accordingly, right?
So we know in the past, like, we call it the instance, we would always treat it as an object. Is that
Yeah, exactly. You can think about this new double 4 over here is simply anonymous objects, like anonymous objects, right? It's simply anonymous object, an object without a name. Okay, right. Okay, guys, any questions about this? Are you comfortable with this? Yes. Yeah. Yes. The question is, can an abstract class extend another abstract class? Yes. But I would say, for the example I'm showing to you, I'm trying to make it simple. So just one level. In practice, you can have as many levels as you like. Right? Questions?
What you know that Polygon not to get area?
Get area?
Whatever you said, the Polygon not to get area.
Polygon not get it?
Dot.
Dot get area? Okay, so you're basically talking about how this code can be run at the runtime. So we will see some code in just a moment. Okay? Okay, we're only trying to see how you can implement the 3 classes, but it's more important to understand how to use them. Yeah. Yeah, correct. Okay, how about let me just give you the preview. What you cannot write at the compiler time. Given this, if you say Polygon P, let's say, P has a static type Polygon. Agree? Good. What can we pass as dynamic type? It can be any of the descendant classes, which include rectangle and triangle. Let me try to strengthen that requirement just a little bit. Any non-abstract descendants can be used as dynamic type. In this case, Polygon itself simply is abstract, so we cannot use it. So now, if you say P is assigned to new Polygon, let me give you all the 3 possibilities. That's one way. We can say P is assigned to new triangle, some argument over here. I just ignore the arguments here. Or you can say P is assigned to new rectangle. And also some argument over here. So 3 possibilities, right? As we learned before. Now, We know that only these two are not abstract, so they can be used as dynamic types. So when you call any method like a getArea, you wouldn't crash. On the other hand, this one over here is simply not going to compile. You just cannot use abstract class as a dynamic type. Okay? So what we learned previously, every class is non-abstract, so that's why we don't have this constraint. But once we add the abstract class and later interface into play, you have to exclude these two possibilities. Exactly. So the first one, again, we try to prove by contradiction. If you allow the first line to compile, that means when you call p.getArea, it's going to crash. So that means we shouldn't allow that to compile in the first place. Right? Yeah. Okay, let's now have a look at some testing code. Right? Let's just go directly to there. Easy one first. Okay? I think that will answer Robbie's question about how we use Polygon. Okay? Dynamically speaking, we can have either rectangle or triangle. Let's try to go over that. The code is quite easy. Okay? So now, first of all, let's go over line by line. First of all, let me just use orange. Maybe pink. Pink would be better. This line here, we simply declare P to be of static type Polygon. Okay? It's a reference. And what about this line over here? What we're doing is we're creating a new object of type rectangle, which is over here. Rectangle, which has sides. And in the case of the rectangle, we're simply going to create an array of size 4, right? As we learned before, of size 4. Okay, you can refer to the code over there. And then since we got 3 and 4, so we're going to fill up 3, 4, 3, 4 over here. That's how we create it. And then we say P is assigned to this particular instance. That means P is now going to point to this particular rectangle. Guys, are we okay? So that means that dynamic type for P at the moment is simply rectangle. Static type remains to be polygon. Okay? And now, if I say P.getParameter, so which version of getParameter is it going to call? Which version? Define where? If I say P.getParameter, how many versions of getParameter anyway? If you look at, yep, exactly this version, the only version that's over here. There's only one version of getParameter. Okay? So that's simply just going to sum up the sides 3 plus 4 plus 3 plus 4. You got 14. That's why you got 14 over here. Okay? On the other hand, if you look at P.getArea, okay? Think about dynamic binding. P over here, the dynamic type is simply rectangle. Now, which version of getArea is it going to call? Rectangle. And let's have a quick look. Rectangle getArea is defined exactly over here. It wouldn't be this version over here, that's abstract, simply nothing there. So just getArea over here, which will be multiply the first side by the second side. And that will simply do 3 multiplied by 4. That's why you get 12. Questions?
Let's say in the rectangular triangle class, you did define the getArea method, and it only relied on the abstract definition that you created.
Good question. So the question was, let's say, let me go back to the previous slide over here. The question was, what if temporarily I simply get rid of this part over here? No getArea over here. If you simply do this one here, Java compiler is going to complain to say that for this class called rectangle, it was not declared as abstract. However, it inherits an abstract method from the Polygon, but you haven't overridden it. That's why it's going to complain. So that's why you got two choices over here. Either you can declare abstract over here in front of the rectangle class, option number 1. But that's not what we want, because we really want to define the getArea in this case. Option number 2, you get rid of the abstract over here, which means we want to make rectangle class concrete, and then put the definition over here, like what we did before. Okay, like here. Make sense? Yeah. Yes.
So the only difference between abstract and the override we used before is like override. You do not need to declare another in the sentence, but if you are using abstract, you always need to.
Yeah, exactly. So now, if you say you extend a class over here and the class is abstract, you got two choices. Either you have to implement all the abstract classes, or sorry, all the abstract method you inherit from the superclass, which is abstract. Option number one. In which case, you don't have to declare this particular class as abstract. Option number two, if you choose to leave one of the abstract methods you inherit still be abstract, you have no choice but leaving abstract for the current class. There are only two options over here. Okay? Okay, guys, any questions? Good. Let's go back to that particular code over here. So now for get area, since we know the dynamic type for P is rectangle, so we're going to call this particular version of get area. Okay? Just 3 by 4. Now let's do some reassignments. What we'll do is we'll say over here, let me use a different color here, green. If we say P is reassigned to new triangle, okay? What it will do is it's going to create a new triangle class over here. If you look at the constructor for triangle in the previous one, the new triangle constructor here is going to take basically 1, 2, and 3 sides, and then assign the sides accordingly, which means over here we simply got 3, 4, and 5. So 3, 4, and 5. Okay? And then P is going to be reassigned to that particular triangle. Rather than pointing to here, P is now going to point to here. So what we have changed is not a static type for P. It remains to be polygon. But the dynamic type has changed from rectangle to triangle. That means now, if we try to do P dot get parameter over here, which version are we calling? Which version? Get parameter. The same one, because there's only one single version for get parameter, which is over here, the same. That one, no question. There's only one version. On the other hand, if you look at P.getArea over here, since we know the dynamic type is triangle over here. So that means we're going to call a different version, even though we're calling the same method, but different version because of dynamic binding. Okay? Now, in this case, you're going to make sure it calls this area. Okay? For those of you who come to the class, which I appreciate, I'll tell you that there's something you are expected to write this afternoon. You have to look at a particular fragment of code. You have to somehow to see which line will illustrate dynamic binding. And then you got to explain to me how the dynamic binding happens. What I expect you to write is to figure out exactly at that point of execution, what's the dynamic type for that particular line, and tell me which version of the method would be called. Okay? Make sense? Good. Only for those of you who come to class. All right, let's go on. Okay, any question about this slide here? Are we okay? Good. Let's go on and see something that's a little bit more complicated. So I will show you some code on the slides, and then we'll analyze the code altogether. If we got more time remaining today, I'll give you more tips for this afternoon. We'll see if we got time. Okay, let's define a new class called Polygon Collector. Okay? Now, we have basically an array of polygon over here, and we got polygons. Now, immediately I got a question for you. We know that very well. The static type for every element in this particular array is polygon. And we know that polygons over here is the so-called polymorphic array, right? That's part of your study for lab test 3. Now, question for you. Dynamically speaking, what are the possible dynamic types for every element in this polygons array? How many? 2 or 3? 2. Can be triangle or rectangle, right? Okay, in this case. Now, let's go on, and then we simply say, if you want to create a polygon, simply say size 10. Okay, just say up to 10 polygons. And then this is how we add a polygon, as before, how you add the students. We simply say the static type for the parameter is simply just polygon. That means you can add anything whose static type is a descending class of polygon, which can be triangle or rectangle. Okay? So you can see nothing is new here, right? The same idea. And then for grow all. Now, let's prepare you well for this afternoon's lab test. All right? If you look at from line number 8 to line number 12, can you see which line is going to illustrate dynamic binding? From line number 8 to line number 12. Or you don't think there's no illustration of dynamic binding, you can also say that. Anyone want to try? Go ahead. Line number 10, okay. You're claiming that line number 10 is going to illustrate dynamic binding. That's correct, but how? Okay, very good. For example, let's say this. If I create a polygon collector objects, let's say I add the first object shape into the collector to be rectangle, and the second object shape to be triangle, right? When I run this particular loop, for the very first iteration, I will get back a polygon of dynamic type rectangle. For the second iteration, I will get back a polygon of type triangle. And you can see that for line number 10, over here, you can see that polygons at position I that grow, right? So that means depending on which dynamic objects I'm talking about, it's going to call the corresponding grow accordingly. Okay, that's how the dynamic type binding is going to work. Similarly, if I simply say polygons I dot get area, that's also going to demonstrate dynamic binding. Okay, good. Okay, so static type, dynamic type. Okay, that's really important to clarify between these two. Okay, so now let's have a look at a test altogether. Okay. Okay, so we do have this. Okay, let's go over that. Again, I want to highlight again for you. If you look at over here, so over here, polygon collector. Okay, that's a new class we're talking about. And then every element in the array is going to be of static type polygon. It's polymorphic array. And then for this line particularly, we know that depending on what dynamic objects we're talking about, it can be rectangle, can be triangle, right? It's going to affect. Okay. Now let's see exactly how the code can be executed. Let's see. What we will do is first of all we create a polygon collector objects. So that's what we have, polygon, let me use green. So polygon collector, so that's collector of type polygon collector. Initially, simply, the counter is simply 0, nothing there just yet. But I'll create an array from 0 to 9, just every element pointing to null. Now, let's see that. The first line over here, collector.add polygon, and then new rectangle. Again, let's practice. Should this line compile or not? Okay, you want to check the argument type should be a descending class of the parameter type, right? The argument type apparently is rectangle. What's the parameter type for add polygon? Well, add polygon is simply over here of type polygon. Is rectangle a descending class of polygon? Yes, so that will compile. Okay, what it will do is it's going to add basically the first elements over here. This is the first elements in the polygons array for the collector. And then we're going to make sure it points to this particular new rectangle objects. So that means it is going to point to over here. Guys, make sense? Okay. Second one. The second one, let's use pink. The second one, the same collector objects over here. And then we say add polygon. Now we're creating a different object here. The same question, should this compile? Yes, because the argument type, which is triangle over here, is a descending class of this parameter type, which is polygon. Okay? So what we'll do is we'll first of all create this particular triangle objects, and then it's going to be 3, 4, and 5. 3, 4, and 5, and then it's the second shape we are adding. So that means the second element over here is going to point to this particular triangle, right? So far we got two shapes. There's one thing I forgot to do. Over here you can see 3 and 4. So we got 3, 4, 3, 4 over here. Okay, we got two shapes. Okay? Now, let's try to do some execution over here. If I do something over here, if I simply say system.out.println, okay, collector.polygons at position 0, which objects am I talking about over here? Well, collector is here, right? Remember we're talking about dot notation, right? Collector.polygons is talking about this particular array, and then I'm talking about position 0, which is over here. And that is referring to this particular rectangle objects. Okay, now when I say this particular object.get parameter, which version of get parameter am I going to call? How many versions of get parameter do we have? Just one version, right? Okay, let me remind you about it. There's only one version over there, which is over here at the Polygon class. Simply sum up all the sides. So what that would do is over here, simply say 3 plus 4 plus 3 plus 4. That's how you get 14. Okay? The next one, if I try the following, the same collector objects over here, the polygons, the same array, and then at position 1. Position 1 is talking about this particular position, right? And that one is referring to a triangle objects. And we say get parameter over here. Now, which version of get parameter are we calling? Well, the same. Get parameter over here. There's only one single version. Okay? But when you get to get area, it's going to be different versions. Depends. Okay, now in this case, it's going to be basically just 3 plus 4 plus 5. That's how you get 12. Okay? Now let's do something more interesting. What we will do is we'll simply say collector.grow all. So grow all is actually a method that we define in the collector class. Let's have a look. The grow all simply just over here, collector. You will simply go over all the shapes. In this case, we go over position 0, position 1, and then for every one of them, it's going to be I can be 0 or it can be 1, right? When I is equal to 0, we're going to say polygons. Let's just do that for the first iteration. Let me just be consistent with the color. The first iteration is going to be polygons at position 0 dot grow. Okay? What this would do is it's going to go to wherever this object is referring to. It is going to refer to position 0, which is this rectangle objects. Okay? And then it's going to refer to the grow method. How many versions of grow do we have? Let's remind you. Okay? There's only one version of grow, which is over here in the polygon. Only one version, which means increment every side by just 1. Okay? And then when we call this particular polygons at position 0, in this case, it's going to be a rectangle that grow. How do we grow the rectangle? Simply go over every side. It used to be 3, 4, 3, 4. Increment every side such that it becomes 4, 5, and 4, 5. That's how we modify the objects, right? That's why after this, when you say get parameter again, it's going to be 18. It's grown. Okay? Let's do something similar. What about the second iteration? For the second iteration for this particular loop, we're going to say polygons. I'll put here. It's going to be polygons at position 1 for the second iteration, dot grow. Now, let's have a look at what's going to happen. Polygons at position 1 over here is referring to this second position here, which is referring to a triangle, right? A different objects over here, triangle. So now it's going to be triangle. If you want to grow the side of the triangle, you're going to call the same version of the grow, which is defined over here, the grow. You simply increment every side by 1. So what you will get is, used to be 3, 4, and 5. It's now 4, 5, and 6. Okay? And then you simply just get a sum up. It will be 15 instead. So it's incremented from 12 to 15. Okay? Guys, are we okay with this? Yes.
Sorry,
Yeah.
Earlier we were talking about, I think it was the grow all, but I'm
Sure.
not exactly sure.
Mhm.
The grow all method where you go through all the polygons and
Yes.
calling grow on each.
Mhm.
Is it's still considered dynamic binding even if both rectangle and
Share the same version.
triangle
Yeah.
share the same
Yeah. The question was, I like the question. Basically, if you look at this line again, let me just go back here. Okay, let me just highlight this line. Basically, you're talking about this particular line over here. I'll just make it clear here. Okay, this line here. Okay, if you think about this line, polygons was declared of type polygon statically. And every position of the same array might store any dynamic type that's descending class of polygon, which can be triangle or rectangle. So now, dynamically speaking, what Java runtime will do for the very first iteration, since we are talking about the first position of the array, so you refer to this particular rectangle, Okay, so they would know that I should really try to go to the version of grow that's in rectangle. Okay, the version of grow in rectangle. However, there's no explicit definition for grow in the rectangle class because it's simply just inherited from the Polygon class over here. So that will simply use that version. So the process of going to the dynamic type and see if there's any method defined over there is dynamic binding. You just want to choose according to dynamic type.
As long as it looks.
You will look, yeah. Basically, the lookup process at the runtime to say, based on what the dynamic type is, I will go there and see either you have a version that's defined in the current class, or it might be the closest ancestor that you're using from, right? Either way. Both are cases for dynamic binding, okay? We'll see another case where you say get area. We'll just see that. Okay, that's about it. Guys, any more questions? Okay. I also make the source code available to you so you can also play with it, okay? Okay, finally, let's say we have another class over here, which is gonna be more fun over here. Let's say so this part I already went over. Let's just go to the second class, okay? So this is a final test for abstract class, okay? So let's say we got a class called Polygon constructor, okay? Let's exercise our understanding about the return value being polymorphic, okay? Over here, let's say we have, so what I will do is I'll show you the class over here, okay? It's over here. So we got a class called Polygon constructor, okay? And then we simply got a single method over there. The static return type is simply Polygon. Dynamically speaking, what can be the objects that's returned from getPolygon, dynamically speaking? What can be rectangle? It can also be triangle, right? Let's see how that can be implemented. So now we simply say, whenever I want to get a polygon, I simply pass an array of sides. Basically, what we will do is, if the array of sides happens to be 3, that means I'm going to return a triangle dynamically. If the array is of size 4, then I'm going to return a rectangle dynamically. Let's not worry about the size being anything else. Let's assume. Okay? Let's not worry about error checking. So what I would say is, let's say I declare the return value of static type polygon. We know that what can be the right-hand side? It can be either rectangle or triangle, right? Conditionally. Now we say if the size array that I pass as input has the length 3, that means I want a triangle, right? I simply say new triangle 0, 1, and 2, different positions, right? Otherwise, if the size.length from the input is simply 4, that means I want a rectangle instead. So that means I will call new rectangle and this, right? Now, you can see that line number 5 and line number 8 illustrate polymorphism. Can you see why? Let me repeat again. Line number 5 and line number 8 illustrate exactly what polymorphism can do for you. Anybody wants to try to explain before I try? Anybody? It's okay to be wrong. Nobody? Yes? Yep, so triangle, line number 5, you can see the new dynamic type. Triangle is a descending class of the left-hand side static type, which was declared at line number 3, polygon, right? And what about line number 8? Same thing, you want to try? Just complete the same statements.
Polygon, or each static type initially is a polygon,
Mm-hmm.
and the new rectangle static type is rectangle.
Mm-hmm.
Rectangle is the descendant polygon.
Yep, true, exactly. The rectangle on line number 8 on the right-hand side is actually a descending class of the static type of P on the left-hand side, which is polygon. Okay, that's kind of the static polymorphism dynamic binding, right? They work. Okay, so now we pretty much understand. So that's about, and then we also got something here. Also void and grow over here, the mutator here. We are getting a polygon object over here, and then we simply call p.grow. Again, polymorphism tells us what we can pass to this grow over here can be either a rectangle or triangle, right? So that's why when you say p.grow at the runtime, dynamic binding is going to make sure they go to the corresponding dynamic type and see which version of grow is going to be called. Okay, but we'll see example. Guys, any question about this definition here? It's very similar to what we did for the student management system that we talked about before in the inheritance lecture. Very similar. So I think repetition might hopefully strengthen your understanding. Okay? Okay, let's see how we can test this particular class quickly. Okay, let's see how we can do that. Okay, it's kind of a look complicated, but let's go over the diagram, okay? You can definitely go over the code. I would suggest you do, okay, after the lab test, before the exam, okay? Quite many things over here. Let's go over one case for you. Again, I'm going to use green to begin with. We have an array of type double, rectangle size 3, 4, 3, 4, okay? Size 4. And then we simply say, we also got a polygon constructor over here, just come, okay? Get polygon. Remember, get polygon is simply defined over here, right? We're going to check what's the size for rectangle size. In this case, well, length will be 4. That means when we try to execute this block of code at the runtime, it's going to match this particular condition, right? The size will just be 4. That means we're going to create a new rectangle and size of the 2. Right? Since we got 3, 4, 3, 4, what they will do is they're going to create a rectangle object accordingly. So we're going to get 3, 4, 3, 4. Okay? Are we okay? Good. Excuse me. And then let's have a look at the instance of. We got 3 instance of checks for you. Why don't we try? Well, you already see the answer, but let's not look at the answer just yet, okay? How do we evaluate instance of? We have to look at the dynamic type for P. In this case, P's dynamic type is, what's the P's dynamic type? Well, remember what we did before, get polygons is going to give a rectangle size, which will return a rectangle object over here. And then we let P assign to it. That means P is now pointing to a rectangle object. Right? So that means dynamic type for P would be rectangle. Now, what does instance of do for you? What does it check? It checks to see if the dynamic type is a descendant class of the classes you put over here, right? So now, is rectangle a descendant class of polygon? Yes. That's why it's check. Is rectangle a descendant class of rectangle? Yes, okay. Is rectangle a descendant class of triangle? No, so that's why it will be false. Okay, questions on this? Okay, good. Now, let's see over here. Let me just check on you for this particular one, okay? Just the get parameter we talked about already. Now, when I say p.getArea, this again illustrates dynamic binding the second time, okay? When I say p.getArea over here, since I know this p over here, the dynamic type is simply rectangle. We're talking about this particular rectangle objects. Now, which version of getArea is it going to call? Because I'm a rectangle, right? Okay? If you look at that very quickly, just to remind you, getArea will just be over here. Okay? Okay, good. Okay, if you do the calculation, it's just going to be 12. Okay, I'm not going to repeat. Okay, one more thing, and then the rest of the, I will show you one more line. When I say constructor, which is polygon constructor, they'll grow, and then P over here. What's going to happen is we're going to call polygon constructor, and then we got a grow method over here, and then we just pass P. Okay, now, why would this particular line compile? Why would it compile? For compilation, you have to look at the static type, right? What's the static type for the arguments over here, P? Well, it was declared, basically, it was declared previously, okay? It was declared in the previous test. When you say polygon, let me just find it for you. So when you study the notes, you will see that. So in the previous notes, you will actually see polygon. I'll show you the decoration. I'm pretty sure I included somewhere. Okay, I will show you quickly. if you look at the test over here, okay, I'll show you here. Okay, that's actually just the first slide. I actually combined the two tests into two separate slides. But polygon that we talk about is simply a static type polygon. Okay, so when you study the slides, you will see. Okay, so now let me just say that over here, this line over here, P over here has the static type polygon. On the other hand, the formal parameter for grow is over here, which is also polygon. Polygon is a descendant class of itself, so that one we should compile. Okay, and then when we try to execute this line over here, which is over here, p.grow, and because this particular argument p is referring to this particular rectangle, right? That means when we try to execute p.grow, because of dynamic binding, it is going to see what's the grow that's defined in rectangle. Which is, well, let's review very quickly. You can definitely refer to here. The grow is, again, there's no explicit grow for rectangle. It's inherited directly from the grow in the polygon, but still dynamic binding, so it's because you still have to look up the dynamic type. Okay? Okay, any question so far? Okay, now the rest of the test would be, we do something that's simply just symmetric. All we're going to do is, rather than returning, so we call the get polygon again, but now we're going to give another array, which is of size 3, 4, and 5. So what that would do is, you're simply going to execute this branch over here, and it's going to return a new triangle instead. And then it's going to be 3, 4, and 5, and then we do the reassignments over here, so P will be referring to this particular object dynamically. That's what we are doing. Okay? And every check will follow in a similar manner. So I'll leave that to you as an exercise. Okay. Guys, any questions? I agree, this code here is more complicated than before, but hopefully you get used to it. Okay. That's kind of the thing you want to get used to when you program in Java, especially got inheritance and OOP, object orientation. Questions on this? Okay, good. What I will do is, I will go over just one more slide about abstract class. Okay, so very quick. So abstract class, basically, you have at least one method that has not been implemented. In our case, get area for the polygon. Okay? And then you may define some common implementation inherited subclass like a grow and also get parameter from polygon into triangle and rectangle. Okay, so you can try the abstract class as a static type, either as a variable p over here, p of type polygon. Or you can say, when you define the parameter for the method, it can be taking a polygon as a static type. Or it can be, you just return a polygon type. Okay, so these are the three use cases for you. Okay? And again, you're not supposed to use the abstract class as a dynamic type, as we said. Okay? Okay. Questions about abstract class? Okay. The next topic will be also quick. I think it will be quicker than the abstract class. It's something called interface. Okay? It's not really the graphical user interface that we talk about in 1022. It's not that. Okay? So don't worry. It's not that complicated. We talk about abstract classes where you got at least one method that can be abstract. The interface simply go for extreme. Interface, you can think about, is simply an abstract class where every method is abstract, basically. Okay? That means none of the methods will be implemented, which means you only have to declare to say this particular class is actually an interface. And you don't have to declare every method to be abstract. It's implicitly known they are abstract. Let's now see some motivating problem together. Okay? Let me just show you this problem over here. Okay. Now, we talk about how you can represent a two-dimensional points, right? What we are used to is simply say something called Cartesian system. So you simply, for any points on a two-dimensional plane, you simply say what's the value for x and what's the value for y. Basically, x is this value over here, and y is the value over here, right? That's so-called a Cartesian system. That's what we are used to, okay? There's another system, which is called polar system. Okay, the polar system basically goes as follows. Let's say we want to represent the same points over here. The way we do it is by saying, rather than using x and y, we're going to use what's the distance between this point here and the origin. Let's call that r. And then what's the angle between this particular line and the x-axis, and let's call that phi. So these are the two things we can get. We can actually store, as attributes. So now, given r and given phi, how can we know the value to fill in for these particular points? For those of you who learn about trigonometry, right? So how can I get this particular distance over here? I can simply do r times cosine phi, right? I assume you know that, okay? Let's not worry about this part, okay? Just assume that's the case, but you can review your math. And how can I get a value for this over here? It's going to be r times sine phi, okay? That means if I only know about r and phi, I can try to represent the same point using r dot cosine phi, and then r times sine phi. So what's the point over here for this particular motivating example? We are saying that if you want to represent a two-dimensional points, I want to say get x and get y, and get x and get y. So there are two possible strategies for me to implement this. Either I can choose Cartesian, in which case I'm going to store x and y as attributes. Right? If I want to get the x point, just return x. I want to get a y point, just return y. There's another alternative strategy. I can use the polar system, in which case I simply just store two different values. I will store the distance between the points and the origin. Let's call it r. I store the second value, which is the angle in radian. Okay, for those of you who learn about trigonometry, it's called radian, the angle over here. Once I store these two values, how can I get x? How can I get y? You just have to do some computation, r times cosine phi, r times sine phi, right? So from the user's point of view, they just want to say get x and get y. But dynamically speaking, if you're using Cartesian, it's going to be implemented x and y. If you're using dynamically polar, it's going to do these two computations. Okay? That's the big picture. So overall, we want to solve the problem for get x and get y on a two-dimensional plane. If you choose Cartesian, you use one way. If you choose polar, you use the other way.
So basically, when we're using polar, we're just representing the point with that two values.
Correct.
So only when we're asking for data, it's two different data.
Correct, that's correct. Yeah, we'll see the code, okay? So now let's go to the code directly, and then there's only one new syntax you have to write. You have to learn. Okay, I'll go to this particular example in just one moment, okay? Now let's see how things will work. Now let's have a look at the code. I kind of put the code and tester all together for you, okay? Now the only new keyword you have to learn is called interface, okay? When you say rather than a class or abstract class, when you say interface, that means implicitly every method is abstract. Since every method is abstract, there's no need to mention abstract. That's kind of the reasoning, okay? So I simply say get x, get y, double, double. Okay, that's the interface. So when do you use an interface? When you have a particular mutator methods or accessor method you want to support, but you got different ways of implementing those methods. You can simply declare the method signature over here as the interface. And then you have a different number of subclasses to actually implement. For example, let's see the first one. We have a class called CartisianPoint, and then it implements, oh, that's another keyword I forgot. Okay, so now rather than saying extends, you had to say implements. Okay, so when you say you want to extend an abstract class, but you will say you want to implement the interface. Okay, so you say implements this particular point interface. Another class called PolarPoint, which implements the points, the same interface, right? You can see implements here, implements here. Now, what do we do? Let's focus on what we store as attributes. For the Cartesian point, we simply double x, double y, the two values of x and y. In the case of polar points, we store the r and the angle phi. Okay, so it's different attribute we're talking about. But now, since we try to implement the same interface over here, we have to make sure every method that's declared in the interface is implemented, get x and get y. But how do we implement them? In the case of Cartesian points, we simply say get x, get y, the same signature, but I'll say return x, return y, right? We're referring to x and y over here. That was easy. That's how we did it before. What about in the case of the polar points? What we can do is, you got 5 and you got r. Exactly what we said before. You can use the cosine and sine from the math class. And then you simply pass the angle over here, the 5 angle, and then times r, right? Exactly what we said over here. In the case of the x value, you say r times cosine 5. In the case of y value, you say r times sine 5. Okay? And the rest is just translating it to the math. One more thing to show you. Again, you can look at get x, get y. So these are the abstract version that's declared in the interface. Okay? But now, in the case of Cartesian points, we got get x, get y. For the polar points, we also get x and get y. But the way we implement them are different. In the case of Cartesian point, just return x, return y. In the case of the polar point, you say do some sine cosine calculation, right? The hidden implementation is different. But from the user interface point of view, it's the same. Get x and get y. Now, what I would do is, I will use some example to show you how polymorphism and then dynamic binding will work. Okay? Now, let's do a little bit math. Okay? Not too heavy, just a little bit. Okay? First of all, can we just take it for granted? Sine 30 degree is 1 over 2. Okay? And cosine 30 degree is this number over here. Okay? If you don't know why, look it up. I'm not going to bother you with that. Just take it for granted. All right? So to set up our test cases, this is what I would do. I will consider a particular triangle, 30 degree, 60 degree, and 90 degree triangle. I will start with this particular side over here to be 2a. Right? I know that for this particular side over here, it's going to be 2a times cosine 30 degree, which is 1 over 2 times square root of 3, right? That's what I would get. Similarly, for this height over here, it's going to be 2a times sine 30 degree, which would be just a. So that means I will simply get 2a, a times square root of 3, and a. Now I can set a to be any number as I like. If I set a to be 10, that means I can get 20 square root of 3, and also 20, right? Something like that. Okay? That's kind of the setup for us. Okay, and you can also see how we can, yeah, that's exactly the detail. You can look at the slides, okay? Now, let's look at the test, which is very brief. Again, we can see polymorphism and dynamic binding. What I would do is, you can see the a over here, I talk about a. I simply set a to be just 5. And then x, which will be the x value, which is going to be a times square root of 3. Okay, a times square root of 3. And then we also got a. Okay, something like that. So now, let's have a look at, first of all, I declare P to be of type point statically. So the static type of P is point. Dynamically, what can it be? Cartesian or polar. Okay? Now, Cartesian or polar. Let's now discuss this example. We only got 4 more lines to discuss. Okay? Now, I want to talk about, again, review polymorphism and dynamic binding. 1, 2, 3, and 4. Which 2 lines demonstrate polymorphism? Polymorphism. Polymorphism basically tells you can assign a particular variable to any of its descendant classes, right? Which lines demonstrate polymorphism? 1 and 3, very good. So 1 and 3 over here are over here and over here. So P can be either assigned to, you can see, let's try. When I say this particular one, P is simply assigned to a new Cartesian point with x and y. That means P is assigning to this particular Cartesian point objects, right, with the corresponding value, right? So some value over here. Let's not worry about the exact values. And then when I go to line number 3 over here, I'm trying to reassign the same variable. Rather than pointing to here, it's going to point to a new object of type polar points. That means it is going to point to here. That's polymorphism. You can just reassign your reference variable to any object that's of descendant class. All right? That's about polymorphism. The other 2 lines are about dynamic binding, which I will highlight in blue. So P dot get X and P dot get X. Let's only look at the blue ones over here, right? Again, let me try to do a little bit further. Let me call this point A. Let me call this point B. Okay, A and B. A and B look the same. They simply say P dot get X and P dot get X, right? Are they going to call the same version of get X? For A, which version is it going to call? For A. Well, if you want to decide for dynamic binding, what's the dynamic type for P at this point? Well, Cartesian point here, right? Okay, Cartesian points. That means get X over here is simply going to call the get X in the Cartesian points. Just return the value for X. That means currently P is pointing to here. If you want to get X, just return whatever value it is over here. Now, if you go to B over here, right, over here, again, P dot get X. Now, after this particular reassignments over here, let me use green. After this particular reassignments, P is now pointing to this polar points, right? Also got some value over here, okay, different value. Now, when I say P dot get X, which version of get X am I calling? The same version or different, right? The dynamic type over here for P, the dynamic type is simply just polar points. That means the get X from here, which will make use of the R and also the phi to calculate the sine cosine, computation over there. And that's going to be whatever value it is. But these 2 points are just the same. Okay? We're just changing from one binding to another. Okay? Now, any question on this? Okay? Let's now, a common question would be, since I can only show you 2 examples to show you abstract class and also interface. So let me give you some general guidance, when to use which. Okay? We have talked about this already. Final slides over here. Okay. So everything we have set already on the iPad. Okay, interface, you can also go over that. Okay, let's now go to conclusion slides. Abstract classes versus interfaces, when to use which. I would say try to keep these 2 examples in mind. In the case of the polygon, rectangle, and triangle, there are certain methods that can be implemented at the polygon level, and there are some methods that can only be implemented at the rectangle or triangle level. If you got scenarios similar to this, use abstract classes. On the other hand, if all the methods cannot be so precisely determined, use interfaces. Okay, let's see. I'll just summarize that. Use interface if there's a common set of functionality, let's say get X and get Y, and then you got different strategies, polar versus Cartesian, and they are simply completely different strategies for you to use. Okay, and then get X and get Y, they are the functionalities. And then you can either use each descending class represents a different implementation strategy, polar or Cartesian. Okay, Cartesian point, we support get X and get Y by using X and Y, right? In the case of the polar points, we support get X and get Y by using R and phi, the angle. What about abstract classes? I would say abstract classes go a little bit not so extreme. If there are only certain methods that can be shared, but certain you want to define at a descending classes level, you use abstract classes, like in the case of the Polygon. Okay, any questions? Yeah, let me take some questions. I do want to make use of 5 minutes talking about lab tests if you are interested. Okay. So thinking this way, so one particular, so the question is, so if we are trying to define an interface over here, what would be the purpose for that? Basically, when I'm declaring an interface, pretty much like, let me just go to the slides here. Okay, let's say here. So let's say if you are the, let's say you're going to give me some programming assignments. You simply say, now, I want you to give me a descending class of the points, and I don't care how you support the 2 methods over here. It can be get X or get Y. So here you can see you're not constraining me how to do the 2 methods, right, over here. So that means for me, as a programmer, I can choose either to use Cartesian or polar. But you simply don't care about which strategy I'm using. just have a common interface over there. Yeah. But for abstract class, usually you have some method that's already implemented, given to the people. Right? Hey guys, any question for abstract class interfaces? That's pretty much what we have to talk about inheritance for this course. So what I will do after lab test today, on Wednesday, we'll use about 4 lectures time to talk about recursion. Okay? Should I give you some tip for this afternoon? Should I stop recording? I should, right?